Yaskawa.
The Sigma 2 SGDH amplifier uses an advanced tuning algorithm that allows the motor to be controlled with unrivaled performance. Internal to the Sigma 2 is a mathematical model of the actual machine based on the machine's mechanical inertia ratio. The inertia ratio is set by the parameter PN103 as a ratio of the load inertia to motor inertia expressed as a percentage. PN103, when set correctly, will properly scale the speed and position loop gains, giving those tuning parameter settings meaningful values and units. This allows the application of simple equations to set those values for maximum servo response. When high performance is required, PN103 must be set correctly. But the question is how to find out what the inertia ratio is. Traditionally, the inertia ratio is calculated when the motor is sized, using the dimensions and density of each component in the load. However, these specifications are often unreliable or unavailable, and machine complexity often makes it impractical even to measure the components of the machine. The amplifier's online auto-tuning algorithm attempts to estimate the inertia ratio as well, but external factors often limit its accuracy. This e-learning module introduces a simple technique that allows the inertia ratio to be calculated using a spreadsheet by measuring a graph of the machine in motion. This is called finding the inertia ratio by graphical analysis. The spreadsheet that Yaskawa has developed for graphical analysis is called Inertia by Graphical Analysis. The main calculations are done under the Worksheet tab. Notice that the final output on the bottom is the value that should be set to the parameter PN103. The calculations are based on the values in the blue and yellow highlighted cells. The blue highlighted cells contain pertinent information on the servo motor being used. This information can be found on the motor nameplate or within SigmaWin 100 when you connect, or by using the product information button. In this case, Yaskawa's Sigma 2 desktop demo is being used. As indicated, the servo motor is the SigmaAH01. Once the motor type is known, its rated torque in Newton meters and rotor inertia in kilogram meters squared must be entered. This information is listed for all Sigma 2 motors under the Motors tab. Please click the Motors tab now. As we can see, our motor, the SigmaAH01, has a rated torque of 0.318 Newton meters and a rotor inertia of 3.6 times 10 to the negative 6 kilogram meters squared. These values must now be entered in the worksheet. With the motor data entered, the remaining 4 items highlighted yellow remain to be entered from graphical data. The peak torque and friction torque produce acceleration torque. The acceleration time and change in speed produce an acceleration rate. To understand how and why to find this data, click on the Theory tab of the workbook. As the explanation reads, the idea behind inertia by graphical analysis is to work the equations of motor sizing backwards to find the inertia of the load using quantities we can measure off the graph. With sizing, we use motor and machine data to calculate what the torque and speed will look like. But with graphical analysis, we measure what the torque and speed look like to calculate the machine data, specifically the load inertia. The key equation used is similar to Newton's law of F equals ma, force equals mass times acceleration. Translated to a rotary system, the equation is T equals J alpha, which tells us that acceleration torque a rotary force, is equal to the total inertia of the system, including the load and motor, the rotary mass, times the angular acceleration. The equation can be solved for load inertia, which when compared to the motor inertia is the inertia ratio. We see from the equation that load inertia depends only on three components: acceleration torque, acceleration rate, and motor inertia. We already found the motor inertia from the chart. The remaining two components can be found by graphing the motor's torque and feedback speed during acceleration. The ideal graph of torque and feedback speed for a trapezoidal move is as shown. To find acceleration torque, the peak torque and friction torque are measured from the graph. The difference between the two is acceleration torque, one of the components in the equation above. To find the acceleration rate, remember that acceleration is just how fast the speed is changing. Change in speed divided by change in time. So pick any 2 points along the speed profile during acceleration, find the speed change and change in time, and the spreadsheet divides them to calculate the acceleration rate. This graphical data, along with the motor data, is all that is needed to solve the equation for load inertia. The next step is to use the SigmaWin 100 trace feature to take a suitable graph of the machine in motion. Click on the trace icon to open up the graphing tool. Click the Setup button to configure trace data. Using the menu items on the left, the graph data can be chosen. It is extremely important that the graph be of torque reference and feedback speed. Torque reference graphs how much torque the motor produces. Feedback speed graphs how fast the motor actually went. Do not choose speed reference or reference pulse speed, since those are commands rather than the actual movement of the motor. Click the Start button to take the graph. Once the graph is displayed, the first thing to notice is that the torque profile is not flat on top as was expected. This is due to poor tuning. The peak torque can be flattened by setting a temporary torque limit just below the peak level observed in this first trace. In this case, the peak torque is 90%, so a limit of 70% would be appropriate. To set this limit, the parameters can be accessed directly using the Online Parameters button at the top. Now the machine's movement can be graphed again with this torque limit in effect. This trace now looks a lot like the ideal one under the Theory tab, and in fact it contains all the information necessary to complete the data in the worksheet. The peak torque was limited to 70%. The friction torque level can be seen by looking more closely at the peak torque trace while the motor was at constant speed. Adjusting the scaling to 1% per division reveals that the torque during the constant speed part of the move is steady around 5%. The data for peak and friction torque can now be entered into the worksheet. First, enter the peak torque. Now enter the friction torque. All that is left to find is a change in speed and a change in time. Let's go back to SigmaWin 100. The graph should be adjusted to look more closely at the acceleration only. Use the cursors to accurately measure the graph. The cursors can be placed anywhere under the constant torque area, but if they are placed at locations where the speed profile crosses one of the trace grid lines, it is easier to see the change in speed between the cursors. The first cursor was placed to intersect at 0 RPMs and the second cursor to intersect at 1500 RPMs. Both cursors lie within the area that the torque is constant at 70%. The cursor data shows us that the time it took for this acceleration is 6.87 milliseconds. Back at the worksheet, you can enter these last two values, 6.87 milliseconds and 1500 RPM. The result is the load to motor inertia ratio and the corresponding value that should be set into PN103. In this case, the inertia ratio is found to be 148%, or about 1.5 to 1. Hopefully you feel confident enough now to go and try this on your own demo or an actual machine. Finding a machine's inertia ratio by graphical analysis has proven to be very repeatable and accurate to within about 10%. For techniques to find even more accurate results, please refer to the Techniques tab of the worksheet. This concludes Yaskawa's e-learning module, Inertia Ratio by Graphical Analysis. Please visit our website for more information.